So in section 6.2, we looked at kind of the basic operations of addition and subtraction. In section 6.3, we're mostly going to be looking at multiplication and division then of rational numbers. So first, a definition of multiplication. If you have numbers a over b and c over d and you multiply, multiplication is much easier than addition. You simply multiply across the top and you multiply across the bottom. Thank you, Emily. So we don't find common denominators, which makes it significantly easier. There's a very cool picture that we can do to represent what's happening with multiplication that you may not have seen before. So I kind of want you to imagine that you have a cake, because the visual imagery for a cake works really well for this picture. So we're going to draw a rectangular cake, not a circle one. That would not be helpful, actually. Rectangular one. And we're going to imagine that this 3/5 is the first one. The 3/5 is the fraction that I'm trying to represent. So I represent the fraction 3/5 in this diagram by taking my vertical length, right, how long it is, and dividing it vertically into 5 pieces. And I'm going to do my best to make it look convincing, but, you know, it's probably not going to. So, yeah, see, it's terrible. Okay, so imagine there's my cake and it's split vertically into 5. And 3/5 would mean I have 3 of these 5 shaded in. And they should all look equal, and of course mine don't, but you have the right idea. Okay, so if you sort of want to think about a picture of what's happening here is that you baked a cake, and after you had your party, there was 3/5 of the cake left. Okay, can everybody picture this happening? So then, of the 3/5 of the cake, 3/4 of it are eaten. So I need 3/4, but not 3/4 of the original rectangle, but 3/4 of what remains. So I'm going to take what is here, and instead of dividing it vertically, because then I start to have a lot of vertical pieces that look funny, I'm going to divide it horizontally. So I'm going to divide horizontally, and I'm going to divide the whole thing, even though I recognize I've only got, the red part left. So I'm dividing it into 4 rows like this. But again, I only have the shaded part left because everything else was eaten. And if I were shading in 3/4 of the red, it would be these 3 rows, or any of the 3 for that matter, but 3 of the rows. So again, let me do some word picture. Baked a cake, and after the first time I had my party, 3/5 it was left. Okay, I bring it out for family dinner time, and after family dinner time, 3/4 of that 3/5 is now left. That's the blue pieces that have not been eaten. Okay? How much of the whole picture is that? Well, we can count the pieces. How many pieces are double shaded with red and blue? 9. Okay? And if, in fact, our pieces had been cut the way that they're sort of now visually cut, how many pieces would we have originally had? 20. And if you take a look at those numbers, that's exactly what happens when you multiply these up here. You multiply across the top, and you multiply across the bottom. 9 out of 20. Okay? So this imagery of this cake works really well for that idea. Some features about multiplication that are useful to us are identities and inverses. So a multiplicative identity is this special number, it's the number 1, where when we multiply by it, it doesn't change things. And in fact, it's kind of like, well, then what's the point? Well, we do know the point because the number 1 can be represented in more than one way except just the number 1, right? We can represent the number 1 as 2 over 2. And that's one of the facts that we use when we found common denominators, is that 1's the same as 2 over 2. So that's a multiplicative identity. The other one then is the multiplicative inverse. And the multiplicative inverse is simply the number that we have to multiply our value by to get back to 1. And in particular, it is the reciprocal. So if we have the number a over b, then the reciprocal of A over B is the flip. It's B over A. And the reason it's the multiplicative inverse is because when I multiply the two numbers together, I get 1, which is the identity. That's what makes it the multiplicative inverse. This whole front page is like definitions, I know. You're super excited, me too. Okay, next one. The distribution property of multiplication over addition, and I could say over subtraction. Looks just like the distribution property when we had whole numbers and integers. So we take our A over B and we multiply it to each of the pieces inside. So the A over B gets multiplied by C over D. The A over B gets multiplied by E over F. Not any different. And then when it comes to solving equations, we want to be able to do a couple other things that we saw the analog to this with addition. We already saw this once before. So if I have two numbers, A over B, and they're equal to C over D, we have some other number, E over F. Not only can I add E over F to each side and not change the values that are equal. I mean, I change them, but I'd make them still equal. But I can also multiply by that on either side, and the values will stay equal. So we can multiply on two sides of an equation and retain equality. Inequality is quite similar. So we also have the ability to multiply on both sides of an inequality. But depending on what the numbers are, it might change the inequality. So here's the same or the similar statement for inequalities. So if we have an inequality where A over B is greater than C over D, and then we multiply by a positive number, that's what this means. E over F is greater than 0, it's positive. So we multiply by a positive number, then it looks just like what happened when we had the equation. Nothing changed. I multiplied by the value, it's still a greater than sign, all is the same. But the second part says, what if I do this? A over B is greater than C over D, but I multiply by a negative. Well, you probably remember that when you multiply by negatives inside of inequalities, the direction of the inequality switches. So instead of being a greater than symbol like it originally was, now it is a less than symbol. And I'd like to show this because I do this when I talk in number theory in chapter 5 as well. But let me just do this with whole numbers and integer values because it's just easier to work with. But the same applies for our rational numbers. If I had the number 2 and the 2 is greater than 1, and we would all say yes, of course it is, right? And then I multiply both sides by a negative 1. Any negative number will work. This becomes negative 2 and this becomes negative 1. But again, if you think about a number line perspective, negative 1 is actually larger than negative 2. Right? It's further along or further to the right-hand side on a number line, so it's bigger. So that's all that's happening when we talk about the inequalities with fractions involved as well. And then the last example says what happens, because these are multiplying by positive or multiplying by negative. So our last definition talks about what happens when you multiply by 0. So, as expected, if you multiply by 0, you get 0. All right, so we're going to do some examples. As we do these examples, it actually asks us on example number 2 and example number 3 to identify properties that we're using. What is it that allows us to do this? We had a similar question in section 6.2, but it didn't ask us for those properties. We mentioned them. I talked about them when we used them, but we didn't write them down. This time we're going to write them down. So as I'm taking a look at this particular problem, 3/4 x equals 1/5. what is it that we need to do in order to get x alone? Okay, so divide by 3/4. In terms of what we're thinking about instead with multiplication, I'm going to suggest we multiply by 4/3, which is the same thing. So we're going to multiply both sides by the reciprocal, or the multiplicative inverse, if you will. And that operation right there is the multiplicative property of equality. That's what says I can do that. Okay? Now when I do that and I multiply the 4/3 times the 3/4 right here, what number does that give me? It gives me 1. Now we don't usually write that out. We're going to right now because I want you to see all those properties that are actually coming into play. There's a 1 there. So what property is that? Well, that's the multiplicative inverse property. That's what gave me a 1. On the right-hand side, it's just multiplication, definition of multiplication. So 4 on top, 15 on bottom. So that was the definition of multiplication on the right. And then what is 1 times x? It's just x. And that has a property as well. That property is the multiplicative identity property. The multiplicative identity property, hang on, I'll just start with property, says that when I multiply things by 1, they don't change. So 1 times x is x. So many properties going on behind the scenes. Ready to try one that has 2 operations in it? Casey's like, I don't know, maybe not. Can we save that for another day? All right. So we have in this one some addition and subtraction. We have some properties back from addition and subtraction, so we're going to identify those as well. So first we need to get all the things with x's on one side and all the things with just the constants on the other side. So I'm going to suggest that we move our x's to the left and subtract the x over 6. So that actually is the additive property of equality. And when I do that, I actually get these two to add to 0, right? And that property is actually the multiplicative, I had it right the first time, additive inverse property. That's why it equals 0. I've used the additive inverse. So on the left now I have 2x over 3 minus x over 6. And I still need to do the same thing with the 1/4. So I have 1 plus the 1/4, and on the other side the 1/2. So I need to move my 1/4. And it's the same thing, right? It's these other, it's these properties again. It's the additive property of equality and then the additive inverse property. So these two right here is, I'm just going to write the word repeat. I've done it twice. I did it with the x's and then I did it with the constants. Yes, ma'am?
Since we're subtracting the 1/2, would it be 0 minus 1/2, or how do we get the addition sign there?
So I was subtracting, oh, is it a negative?
Yeah.
I'm sorry, because my circle that I circled with covered it up, and so I didn't have it written down right. Now it's negative. Thanks for catching that. We would have had a problem later. That's good. Okay. So on the left-hand side, these, of course, add to 0. On the right-hand side, on the left-hand side, I now need to make some combinations of things. So I have 2x over 3. And you can combine some of these steps together, but I'm just going to show them all out separately for the time being. And I have negative 1/2 minus 1/4. So far, so good? Okay, adding and subtracting fractions. We did that last class period. So on the 2x over 3, if I multiply the denominator by 2, I'll get the 6, so my denominators will match. So that will give me 4x minus x over 6. Oh, and I should say the reason my zeros are going away, I mentioned it when I did it before, so I'll mention it here again, is my zeros are going away because that's the additive in identity property, right? It says that I have the number 0, and the number 0 has the ability to be added to something and not change its value, just like the number 1 has the ability to be multiplied and not change its value. I'm doing some definitions of multiplication at the moment. I don't mean multiplication, definitions of addition at the moment, right? Where I'm taking and I'm finding this common denominator business. This is what happens when we are doing addition. I'm doing it on the right-hand side as well. So I'm going to multiply this denominator by 2 so that they'll become a 4. So on the right-hand side now I have negative 2 minus 1 over 4. So we'll do some simplification. This gives me 3x over 6 on the left and negative 3/4 on the right. A couple different things we could do. What do you guys see? Simplify. Are you thinking the 3 over 6 simplifying? Yeah, that's what I do too. I would go ahead and simplify the 3 over 6, so it should be x over 2 equals negative 3/4. And then I need to get this to have x alone, so what am I going to do with that 2? Yeah, I'm going to multiply by it. And once again, what we see happening is that multiplicative inverse coming into play. I won't list it again. We've already listed it once, but it's coming into play yet again. So I have x on the left, and then I have the negative 3 times 2, so negative 6 over 4 on the right. Can't quite leave it there. There is a little problem. What do I need to do before I'm finished? Yeah, I need to simplify. So this will be divided by 2, each of them. So my x is actually equal to negative 3/2. Lots and lots of properties. You definitely don't have to show every single piece of the steps that I've written there. But you should be recognizing more and more of those properties that play behind the scenes as you're doing the problems and thinking about them. So let's talk about division next. So if we have two numbers, a over b and c over d, that we're wanting to divide, so a over b divided by c over d, then it is the unique number, oh, I have a typo in what I wrote on the paper. It's the unique number e over f, if and only if you can multiply that e over f to the other side and achieve the same result. C over d times e over f is equal to a over b. So as with other times, I'm going to just show it to you in terms of some whole numbers because it's easier to manipulate them to see. But the reason that 6 divided by 3 is equal to 2 is because 2 times 3 is equal to 6. And that's what this is saying. This is a direct, throwback to multiplication. There's a cool algorithm for division that sometimes people don't know why it works. But it says the following. If I have a over b divided by c over d, instead of doing division, I can multiply by the reciprocal. Imagine it's something that you remember you can do. But I think that it kind of begs the question of, well, why can I do that? I mean, great, sure, I can turn it into something else I know how to do, but why? Why does that work? So I'm going to show you, because it's really not hard to actually justify why it works. So if we have a over b divided by c over d, what I'm going to do is I'm going to rewrite that division with the line and the 2 dots as a division bar. So we're going to write a over b, and we're going to write the division like this. Okay, so admittedly, it doesn't look very good, but it is an alternate way of writing the same thing. So in algebra, when you talk about this is called a complex fraction. Talk about complex fractions. What you usually do is you work on ways to eliminate the complex fractions so that it has a single numerator and a single denominator when you're done. So when they're written this way, where it's a single fraction on top and a single fraction on bottom without any like addition or subtraction involved or anything like that, the way that we actually can get rid of that c over d in the denominator is multiplying by d over c. And the reason that's true is because what is c over d times d over c? Yeah, that's the multiplicative inverse at play there. I'm going to actually equal the number 1. So when I do this, I end up with a over b times d over c over 1, which is the same thing as a over b times d over c, which is what I wanted to end with anyway. So it's really just happening because there's that multiplicative inverse property coming into play yet again. All right, division with fractions can be a little confusing. And so what I'd like to do is to talk about what it means to divide by fractions, again, by going back to the idea of what it means to divide with whole numbers. So if you describe what is meant by 6 divided by 2, there's a couple of different ways that you can describe it. One option is that you can describe 6 objects where you break them into 2 groups, right? I have 6 objects and I divide them into 2 separate groups. The other way that you can describe it is where you have 6 objects and you make groups that have size 2. So I put 2 in every group, and the answer is the number of groups I'm done with. Okay, does that make sense to everybody? If you haven't had number theory, that is something we talk about in number theories. It's 2 different types of partitions. So it's actually really nice to think about it that way for the following. To think about the second way I just mentioned when we're thinking about fractional division. So we're going to draw 6 circles. I hesitate to say they're cookies because you might be hungry, but we can make them cookies if you'd like. So I have 6. And I'm actually going to go with that whole idea of I'm making them into groups of 2 because it will connect better with our fractions. So I have 3 groups of 2. And I'm going to write the word size in here again. You'll see why. 6 in groups of size 2. So this lends itself exactly to what happens when we divide by fractions. So we're going to do the same thing with 6 divided by 1/2. So I'm going to draw my 6 cookies. But now what this is saying I want, instead of groups of size 2, is I want groups what? What's that number? 0.5 or 1/2 if we do it in fraction form. You're right, yeah. We want groups of size 1/2. Okay? So if you've ever been to McAllister's or City Bites, they have these gigantic cookies, right? So imagine that size is a cookie where you're splitting them into half portions instead. That's what's happening here. And you're asking yourself, well, over here, if I had 6 cookies and I grew up in groups of 2 and I handed out these little baggies, I can feed 3 people, right? Well, if I have the gigantic cookies and I make groups of size 1/2 and I make, put those in individual baggies, how many people can have one of my baggies of cookies? 12, right? There are 12 halves there. So that's actually what's happening here when I say that I've got 6 divided by 1/2. Numerically speaking, from a moment ago, we recognize that becomes 6 times 1 over 2, or 2 over 1, which is 12. This is a visual to sort of justify why that's happening. I've got 12 groups that are size 1/2, and that's where how my 6 was split instead. Okay. So there's sort of an aside that happens in this section It's a related idea, but it's not directly related to the title, which says multiplication and division of rational numbers. And what we're going to talk about for the remainder of this section is actually exponents. So, again, in number theory, how many of you have had number theory, by the way? Just you? Nobody else has? Okay, so a couple people have. So we talk about this for the first time in number theory. That's the first time it shows up in the book, sort of sequentially. It's in chapter 3, I think, in the book. But it comes back up in chapter 6, and it actually adds to what we talk about. So first, a definition of exponents. So for rational number a and a natural number n, a to the n is a multiplied n times. Right, so what is 4 squared? It's 4 times 4. What is 4 cubed? It's 4 times 4 times 4. And we have 6 basic properties that we're going to discuss, and there's a couple more on the next page as well. These are my 6 basic properties. What I want to do first is to just tell you what the property is, and then I'm actually going to talk to you about why it works. We do that a lot in this class, not because you're going to have a lot of kids asking you every now and then why something works, but because when there's that one kid, you know, you've learned it somewhere along the way, and you can find the answer again easily, and once you do, you'll know how to make sense of it. Okay? You're not going to remember it, that's okay, but you'll remember you learned it. So the first property on everything, you may remember some things. I'm not suggesting you're never remembering anything I'm teaching you. I hope that's not true. Goodness gracious. The first one, a to the m times a to the n is a to the m plus n. We add exponents. So on the first one, if it's multiplication and we add exponents, what do you think happens when we have division? You subtract exponents. Yep. So this is a to the m minus n. So that's like an intuitive what I think should happen, and it does. Number 3 is a little different than number 1. On number 1, you actually have the base repeated, right? It's a to the m, a to the n. But on number 3, you have the a to the m, and then it's raised to the power n. Okay? So a little bit different sort of patterning. And when that happens, we actually multiply our exponents together as opposed to adding them. 4 and 5 are something akin to the distribution property. So distribution is actually multiplication over addition or subtraction. But it works very similarly with these exponents over multiplication. So my m applies to each of the pieces inside because they're multiplied. So it's a to the m and b to the m. Just like with multiplication, division identical, I will distribute the m across the division sign through the parentheses, so I have a to the m over b to the m. And the only difference on part D, or what do we have here, 6, rather part 6, is that we have a negative exponent. Okay, so it still does this distribution, but negative exponents flip things upside down. So if they're negative and they're in the numerator, they move to the denominator and vice versa. So I'm going to show it to you just the way the answer ends up being, but then I'll show you just one piece underneath of sort of the intermediate thought process. Intermediately, this looks like a to the negative m over b to the negative m, and then the fact that the negatives are in the exponents flip the numerator and the denominator upside down. All right, so when you get to your homework, you're just going to use these properties, okay? What I'm about to show you next is not for me to have you repeat on the homework back to me. That's not the point. But I do want you to see where the things come from. So these are the whys, or the explanations behind what's happening. So y'all know that this is addition because I just told you a moment ago. So I'm going to justify for you with an example why that makes sense. So we're going to consider having a to the third times a to the fourth. Okay, so a to the third means a times a times a. A to the fourth means a times a times a times a, 4 of them, right? How many is that? 7. So how do you get from 3 and 4 to 7? You add. Okay. We can do the same kind of thing here with our division one. So it's subtraction. And we will do the example of a to the fifth, I used mine, a to the fifth over a squared. So a to the fifth is 5 a's, 1, 2, 3, 4, and 5. And a squared is 2 a's. All right. And then division, when multiplication is included, and we've actually talked about this, like this idea of reducing in fractions allows me to cancel multiplicative terms on the top and the bottom when they match. That leaves me with 3 a's, so that's a cubed. And how do we get from 5 and 2 to 3? We subtract. Okay, the third one we multiplied, like so. So my example, we're going to do a cubed squared. So a cubed means I have 3 a's, and it's supposed to be squared. That squared on the outside means I have what's inside written twice. So I have 3 a's followed by 3 a's. How many is that? 6. And how do I get from 3 and 2 to 6? Multiply. Number 4 is distributing a to the m, b to the m. And we will do ab to the third. So ab to the third would mean that I have ab times ab times AB. And we talked in, it may have been section 6.1, about some properties of rational numbers that allow us to switch orders of things. We did it with addition, right? 3 plus 2 is the same as 2 plus 3. 3 times 2 is the same as 2 times 3. It's called the commutative property. So we're going to use the commutative property along with the associative property, which allows me to regroup things and to put all the A's together, and then to put all the B's together. So that's the commutative and associative properties at play multiple times. And sure enough, when I do that, I have a cubed, b cubed. And there's nothing special about the fact that I did it for 3. I could do it for however many exponent I want. Much the same way on number 5, a to the m over b to the m. If I have a over b cubed, it's even more direct, right? Because it's really just the definition of multiplication. What do? I multiply across the top, that's a cubed, and multiply across the bottom, it's b cubed. No need to even regroup anything or anything like that. Number 6, we discussed as being b to the m over a to the m. And we will use, 3 is a good number to use, so I use it a lot. We'll use -3. And what I'd like for you to think about is that -3 has 2 components. It has the component that's the 3 and the component that's the negative. So I'm going to separate them by writing this as a over b to the third, and then all of that raised to the -1. So I've separated out the -3 into the -1 and the +3. So we already did the a cubed over b cubed from above. We already had that property. And then a -1 exponent means the reciprocal. By definition, that's what it means when you have a -1 exponent. So when I reciprocate this, I get b cubed on top and a cubed on bottom. Okay, I have 2 more properties at play. Does anybody remember what a to the 0 is? It is a number 1. This is a fabulous one to show you why for, because I think it feels a little mysterious. How, when I raise something to a 0 power, do I get 1? That's a lot of faith right there if you don't have a good justification for that, because that looks funny. Some of the other ones you're like, oh yeah, I can see how that makes sense without even sort of arguing it to somebody. It seems reasonable. This one seems a little bit like smoke and mirrors. But it's pretty easy to show. So we're going to take a to the 0. This is an actual proof, not just like me trying to justify like the last ones. This is an actual proof. And we're going to take the number 0 and we're going to rewrite 0 in a different way. In particular, I can write the 0, actually I'll use numbers, as a 3 minus 3. 3 minus 3 is 0, right? Yeah, no problem. And then what we're going to actually do is we're going to use property number 2 over here. I passed it. In reverse. We're starting with something that looks like this, and I'm going to rewrite it as division. Okay? So, over here, I can now rewrite this as a cubed over a cubed. And what is any value divided by itself? 1. And voila, a to the 0 is 1. And it's just a couple of steps. And the last one is quite similar to number 6. It talks about what happens when you have just a single value a raised to the power negative n. This actually becomes 1 over a to the n. And as an example, we'll do a to the negative 3. So again, we can talk about this negative separated into a negative 1 and a 3. And I separated it this time this way. I did it the other way the last time. It doesn't really matter. But the a to the negative 1 means the reciprocal, and the reciprocal of a is 1 over a. And then if I apply my 3 to each of the terms, 1 cubed is 1, and a cubed is a cubed. So 1 over a cubed. So that's a really good place for us to stop. We haven't started any of the examples yet. So we'll finish the examples from these next time. There's a few of them on there. And then we will move into 6.4. When I get back to my office, I will adjust the due date inside of Canvas. If I don't, feel free to email me and tell me you forgot to adjust the due date. But we'll get that adjusted. So the homework for this will not be due on Monday. It will be due on Wednesday instead. Have a great weekend.